Are there any questions over the assignments thus far? Questions? Yes. Finished? Okay. Oh, okay. Yeah, well, 311 and 312 were technically on the same page. Number 3? So this is 311. Problem number 3. So whenever we factor, when we go through factoring, there's 5 main steps. Step number 1, greatest common factor. And really with any factoring, that's what we should always be looking for, is the greatest common factor. And if we look at this here, 3x squared, 3x, and 6, there's a greatest common factor of 3. And we essentially divide it out of each term. So if I divide 3 out of 3x squared, we're left with x squared. 3 divided out of 3x is x. And 3 divided out of 6 is 2. We divide each one by 3. Questions on this here? Feel good so far? Number 3 off 311.
Is this right here, the homework?
For 3, no, that's the note sheet.
Oh.
That one's the note sheet from Friday.
Note sheet and the homework.
Yeah.
That's the homework. Where? I never got one. I wonder if I did.
If you do find the other one by chance, bring it back. That way.
I don't remember.
Now, this takes us steps 1 and 2. Because since we don't have any other greatest common factors, we'll do 2 sets of parentheses with 3 spaces. Our next step is to find the sign. To determine the sign, if the third term is positive, the signs are the same and they match the sign of the middle term. If the third term is negative, our signs are opposite. So since this one here is -2, the negative tells us the signs are opposite. One's going to be positive, one is going to be negative. That brings us to step number 4, the factors of the first and third term. The only factors of x squared are x and x. Since we don't have a number in front of it other than 1, we're just having x and x. Factors of 2 are 1 and 2. 1 and 2, 2 and 1. We can put it in either place. I just pick a spot and put them in. Because our last step, step number 5, is to check. So we'll multiply this out here. Now personally, I don't multiply our x times x because according to some textbooks or some methods, we should multiply the whole thing out and check it. But our x times x is x squared because, well, we got it from the factors of x squared, so those should go back to x squared. Same thing's true with 1 and -2. They should multiply together to give us -2 because that's where we got them from. The only way that x and x or 1 and 2 would not multiply back to be what we got is because we got the wrong factors in there to begin with. Now, at this point here, if we check it, x times -2 is -2x. 1 times x is plus x. And -2x plus x is -x. Is that the middle term we wanted? Well, no. It is the correct number, but wrong sign. And whenever we have the correct number, but wrong sign, just flip the signs. And if we check this again, x times 2 is positive 2x. -1 times x is -x, which does indeed give us the positive x that we wanted. So these are our factors here. Number 3 on 311. Any other questions over the homework? Question over any of the other homework assignments? Okay. What we're going over today is the difference of perfect squares. Now there's 2 types, or there's a few. One of them that has a specific pattern is this one here. The difference of perfect squares states that if we have a algebraic expression, we have a quadratic in the form of a squared minus b squared. It factors to a plus b times a minus b every single time. This works every single time if we have a difference of perfect squares. An example of this would be x squared minus 9 squared. Now what they did in that second step next to it is they rewrote it as what each term being squared is in terms of a and b. Well, what times itself is x squared? Well, x, because x times x is x squared. And really what we're saying is that we have x squared. And what times itself is 9? Well, 3. So we have 3 squared. So it's telling us the value of a, what would go at a spot in both cases, is x. It's what term being squared gives us the first spot. So in this example here, a is x, b is 3. So we're plugging it in this form, a plus b times a minus b, which would indeed give us x plus 3 times x minus 3. Pretty much. Yeah, it's really fine square root and plugging it in, yeah. Well, the only thing that is, if there's a greatest common factor, we might have to pull it out before it'll work, but let's look at this first one here. We want to factor x squared minus 25. So obviously this is a difference of perfect squares, otherwise it wouldn't be included. But when we look at this here, x squared is it a perfect square? Well, yes, x times x would give us x squared, so it is a perfect square. Minus, well, 25 is a perfect square, yes? What times itself is 25? 5. So we could rewrite this out as x squared minus 5 squared. And the reason we're writing it out this way is to follow the form a squared minus b squared. Because by definition, a squared minus b squared factors to a minus b times a plus b. Or we could say a plus b times a minus b. One of the signs will be positive, one is negative. And in our case here, a is x and b is 5. A is our first term, b is our second. So in this place, x is our first term, b is our second for this form. So when we factor this, when we have a minus b, it would be x minus 5. Then we have a plus b, it would be x plus 5. That's it. So factoring x squared minus 25 factors to x plus 5 times x minus 5. That's it. Let's look at the next one, 4z squared minus 1. So again, we're still using the form of a squared minus b squared equals a minus b times a plus b. And really, we could have said a plus b times a minus b. Those are the same thing. It's just flipped. Now, looking at this here, we do need the values of a and b. So well, the first question really is 4z squared minus 1 a difference of perfect squares? Is 1 a perfect square? What times itself is 1? 1. 1's actually a perfect any root, because no matter how many times we multiply 1 by itself, it's still 1. So you can actually take the millionth root of 1, millionths, and it's still just 1. One of those interesting ones. So 1 is a perfect square, And it actually works out that we just have 1 squared. The value of b is, well, 1. Exactly, because 4z squared, we're trying to see what times itself is 4z squared. Well, the z squared would just be z. And what times itself is 4? 2z squared, 2z times 2z is 4z squared. So our value of a in this case would be 2z. And the value of b is 1. So when we factor this, a minus b would be 2z minus 1. A plus b would be 2z plus 1. And that's it. Questions on this here? Now I'm going to multiply this out. You don't have to write this down. I'm just kind of going back and showing. 2z times 2z we've already said is 4z squared. 2z times 1 is plus 2z. Negative 1 times 2z is negative 2z. And negative 1 times positive 1 is negative 1. Now this does look like we have more terms than what we started with, but 2z minus 2z is 0. So that's gone, leaving us with 4z squared minus 1. Is that what we started with? Yeah. So it does factor. Questions on this here? Now, do we have to write the value of a and b every time? Well, no. Because once we get used to this and once we see the pattern, because hopefully I think y'all are starting to see the pattern of how this works, yes, it's going to be a little bit easier. Because if we factor x squared minus 64, x squared minus 64, well, x squared is just x squared, yeah. Because there's no other number with it. What times itself is x squared? Well, that'd be x. X times x is x squared. What times itself is 64? 8. So we could rewrite this as x in parentheses squared minus 8 squared. In this case, a is x and b is 8. So how would this factor? Our first set of parentheses would be what? X times, yes. And we know this is a difference of perfect squares because x squared is a perfect square, 64 is a perfect square. We know it's a difference because there's a subtraction in the middle. Okay. Questions on this here? X squared minus 36. Well, we do have subtraction still, yes? Is x squared a perfect square? Yes. Is 36 a perfect square? Okay. And what we're going to get is 2 sets of parentheses. One of them is going to have a subtraction. The other is going to have a plus. Well, what would go in the first spots? So we'd have an x here and an x here, yes? What times itself is 36? So we'd have 6 and, so x minus 6 times x plus 6. That's it. Questions on this here? Questions on anything we've done so far? 100 minus m squared. Is this a difference of perfect squares? Well, yes, because that's the whole lesson today, isn't it? What times itself is 100? What times itself is m squared? M. Since it is a difference of perfect squares, we will have plus and minus. I did flip it from the previous one. I put plus first instead of minus. But if you put minus first, that's perfectly fine too. What would go in the first spots here? What number came first? 100, so we would have 10 and 10. M came second, so we would have m and m. Because in this case, A is our 10 and B is our M. We don't necessarily have to have the M first, so we do have this here. Now technically, even if you did write it as M plus 10 times M minus 10, you would be halfway right. Because 10 plus M and M plus 10 are the same thing. But the second one would be a little bit off. Questions on this here? You're starting to get the hang of how this works. 9n squared minus 16. We know it's a difference. Is 9n squared a perfect square? Because 3n squared, 3n times 3n, well, 3 times 3 is 9. N times n is n squared. What times itself is 16? 4. So we'll have our plus and minus. Since 9n squared went first, our 3n and 3n will go first. Since 16 went second, our 4 and 4 will go second. Questions on this here? Questions on any of this so far? Sixteen h squared minus 49. 16h squared. 16 is a perfect square. It's 4 and 4. H squared is, well, h and h. 49. 7 and 7. So we can say this is what? 4h plus 7 times 4h minus 7. The order in which we write it doesn't really matter. We can have 4h minus 7 times 4h plus 7, or 4h plus 7 times 4h minus 7. And if you do not have most of your perfect squares memorized, calculator will do it just fine. We're just taking the square root. The square root of 16 is 4. Square root of 49 is 7. The calculator will do those for us. Yes?
When we had the number first, why did it have to be plus and then minus?
For here, or
It was the.
here, the M went second because it's second here.
Oh yeah, but why did we have to put the plus?
We didn't.
Okay, so it could have come other way.
Mm-hmm.
I thought you were saying it.
Well, it cannot be, because M plus 10 is fine. Because 10 plus M, M plus 10, either way works, because addition is closed.
Yeah, but minus.
M minus 10 would not be right, because you're getting half of it. Now, the reason this is, and I can multiply this out and kind of show you, because our M times M would be M squared. M times negative 10 would be negative 10M. Negative 10. Right. Well, actually a little bit of the signs, and it's mainly for this here. Because M minus 10 is not the same as 10 minus M. Because having it written this way would give us M squared minus 100, not 100 minus M squared.
Earlier I got confused because I thought you were saying that.
To write it with M first, this would need to be changed to positive 10 and negative M. That's the only way that would work. Might as well just leave it as this here, otherwise we start. Most have trouble with negatives as they are, let alone trying to rewrite it that way. You're welcome. Any other questions? 25b squared minus 36. Because 25 is 5b, 36 is, so we'd have 5b 6 times 5b plus 6. Questions on this here? We were ready for the next one. So we feel pretty comfortable with this here. Because really this is all revolving around our perfect squares. Because once we find the perfect square of each term, plus and minus each of those terms. Now, there can be some with greatest common factors. If there is a greatest common factor, we do have to factor it out if it's not working out. Minus 50x squared minus 98. This isn't in your notes. Y'all can follow along with this here. Now 50, we need to determine if it is a perfect square. Square root of 50 is 5 square root of 2. Square root of 98 is, well, neither one of these is perfect squares because square root of 2. It's telling us it does not simplify nicely. If it had given us 5 and 7, that would have been nice to begin with. So there is a chance that this is still a difference of perfect squares. But if we look at 50 and 98, is there a greatest common factor? Well, 2 does work, and we could factor it out. If I factor 2 out of 50, we have 25x squared minus is 25x squared a difference of perfect squares? 25 is 5 and 5, yes. 49 is 7 and 7. Sometimes we'll still have a difference of perfect squares, but we might need to pull a perfect square, or not a perfect square, a greatest common factor out to get there. Questions on this here? 16, 64. We'll do one more. Squared minus make sure that's right. Nope, not 27. $64x squared minus 36. So I'm going to do greatest common factor first. 4 will go into both 64 and 36. I think y'all can see 64, or not 30, 36 better than 64. But if I factor a 4 out, we'd have 16x squared minus 9. Well, 16 is a perfect square. We've seen it already today. We get this here. But the reason I do show this is, as y'all were saying or already pointing out, 64 is 8 and 36 is 6. It still works, and it seems odd that it does, yes? What was the greatest common factor I pulled out originally? Is 4 a perfect square? This is one of those cases, because 4 is a perfect square, it still works. It's still a difference of perfect squares. It's just that 4 is split up 2 and 2 amongst the two factors. Still works, still factors. It's not technically the simplest form, but it still works. Does that make sense? I will take, if this does show up, I'd take the 8x minus 6, 8x plus 6, but I would write in the fact that we could simplify it. Now, the reason it didn't work on the other one is the greatest common factor is 2 a perfect square. No, because there's nothing multiplied by 2 that would give us 2 that's a nice number. Nothing multiplied by itself is 2. Cross-country girls need to change and get to the football field. So does this kind of make sense why this one works and the other doesn't? The other half of this. Evaluate a numerical expression. So use a pattern, special product pattern to evaluate 54 squared minus 48 squared. Now, if we were doing this, especially without a calculator, and we didn't know the special, or our difference of perfect squares, I would have to figure out what 54 squared is, figure out what 28 squared, or 48 squared is, and then subtract the two numbers from each other. Now, our difference of perfect squares, guys, says that a squared minus b squared is equal to a plus b times a minus b. And what we have for this here is 54 squared minus 48 squared. Well, for us, a is 54, b is 48. So what we're saying is that I have 54 minus 48 times 54 plus 48. Well, 54 minus 48 is 6. 54 plus 48, 102. Then we're going to multiply 102 and 6. Questions on this here? So if we want to evaluate this expression, we're saying 68 minus 62 times 68 plus 62. Well, 68 minus 62 incidentally is 6. 68 plus 62 is 130. And if we multiply by 6, 0, 8, 7. We get 780.
Nice.
68 squared minus 62 squared. Yeah. I mean, realistically, the calculator will do this for us. We don't have to do this. Yeah. Questions on this here?